So here is my team, 1027. We are working on problem C. So my group team members is Aditya Data from Georgia Tech, Yushong from University of Portland, and Jinder Song from New Michigan. And that is our introduction. We are introduced like predators and prey have been in the world for a long time. And under that situation, prey had anti-predatory defense mechanics under predators. And we are interested in how humans act on these environments. And basically, we are making 5 or at least 5 assumptions. First assumption is human populations grows logistically, but we also later we add some fixed like with the death rate. And also we believe climate change has actions about the capacities of the human population. And we also believe the food is substance under the human population, and humans are not attacked for those animals, but that is in the other way around. So we are listing for some questions, and we're interested in how humans do in that kind of long standard systems. And we also interested how this anti-predatory mechanics works, and also how the climate in effects on the environments, and also like how human reactions in this environment works. And also, what if human lives? And basically, we're introducing a 2-dimensional competition mode, where we introduce for the prey and the predator. We're using Y to predict prey and X to predict for predator. We are interested in how they react to each other, so we assume there is a time dependence. So first, we're listing for dy dt, which represent for the change of the population of prey, which equal to a long linear equation, and so for the predator. And we're using A to represent for birth rate, B for fraction of eaten, C for conversions, D for death rate. And the right side is the graph.
One of our primary assumptions is that humans actually act as predators for predators. So we made this assumption because it's observed that humans lead to reduction of native predator populations, or at least to reduction of activities of native predators. That's because domestication restricts their food supply. And because of this, anti-predatory behavior in domesticated animals also decreases, which is the main focus of our research. So therefore, our assumption implies that in the Lotka-Volterra equations, humans actually act as predators and predators act as prey. So we made the necessary replacements in the interspecific competition model, and these are the equations we came up with. However, we learned that human populations do not actually follow the interspecific competition model, but instead they grow logistically with a certain death rate. So we incorporated death rate into a logistic growth model and came up with a new dx upon dt equation, which we incorporated into our old model and came up with the final equation for d capital Y upon dx on the last line, which actually represents the rate of change in anti-predatory phenotypes with respect to human populations. So another factor which we incorporated into a model a bit later is climate change. We've assumed that climate change is, while not directly related to a model, it does impact the carrying capacity K of an area, which plays an important role in the logistic growth model. Uh, so using simple polynomial regression, we came up with a time-dependent equation for K, which is shown below. We also added a proportionality constant, which is one of our assumptions actually. So incorporating this change into a model, or actually the time-dependent K value into a model, uh, and simplifying the model, we get these equations, or actually the final equation. One of the main problems we aimed to solve, or one of the main questions we aim to solve in our research and our work was what happens if humans leave? Is permanent damage already done to the populations, the prey population, or can they recover? So for that, we found what happens to a model as X, or the human population tends to 0. And we took the magnitude of what we got and analyzed that for getting some results. And the results we got were that the response of different populations to humans leaving after domestication actually depends on the species itself, specifically on two features. For example, if that species has a predator which has a greater birth rate, it will actually recover and adapt to the wild once again faster than other species. And the other factor which it depends on is the relation between anti-predatory behavior and predatory populations. The greater this relation, represented by the constant K1 in our equation, is the better the chances of that population, that prey population, once again adapting to the wild are. There is evidence for our theory in the real world. We found that while normal sheep find it difficult to adapt to the wild, certain sheep living in rocky conditions actually find it easier. And we think that this could be because the rocky conditions provide an additional incentive to adapt, just like the greater predator birth, as postulated by our results and model.
So there are some limitations of our models. So for example, a lot of variables are considered, like the level of human interaction and the environment or the specific environment the animals live has not been considered as well. Also, another variable is the regions of animal, and we also come up with a model for that, and we can later add to our model. And this is a exponential decay, and the final result we got after some data cleaning is as this. For y being the variable representing the percentage of the mean value of the Virginia's value, and x being the generation. And due to the complexity of the model, we have to assume that something are constant and not time dependent. For example, birth rates change according to the demographic model, but we assume them to be constant. Also, another unrealistic assumption was that all prey are domestic and find enough food. This could not be the case, and some prey might still not be domesticated. There's not a reference to evaluate the accuracy of our model, and our prediction and only theoretical evidence and arguments can be cited. So the conclusion is our model is a very general one. At this stage, it does not have evidence of validity, and in the real world, in terms of anti-predatory behavior after humans live. There are limitations and a number of assumptions, but the real-world application could be a possibility if some more work is done in terms of data collection.
So these are our references, and yeah, thank you.
Thank you.